In this video, we are going to explore the concept of oxidation and reduction reactions. Oxidation and reduction reactions are going to be a subclass of reactions that can be observed within the context of combination reactions, decomposition reactions, single replacement reactions, and combustion reactions. The only type of reaction that does not undergo oxidation and reduction is going to be double replacement reactions. What happens overall is that a combination reaction at times, or it could be single replacement, it could be decomposition, so on and so forth, they are going to have an exchange of electrons. In this exchange of electrons, somebody's going to lose electrons and somebody's going to gain electrons, and that's what leads to the oxidation and reduction. Oxidation and reduction reactions actually are very important because they provide us with energy from food. So biologically, when we are going through the process of generating that chemical energy that is derived from fat, from carbohydrates, from proteins, our body actually performs oxidation reduction reactions. And we're going to see that later when we do biochemistry. Oxidation reduction reactions are also important in batteries because it's what produces the electrical energy that is derived from those substances. Now, an example of an oxidation reduction reaction actually happens in one of the monuments in our country. So when we look at the Statue of Liberty, the Statue of Liberty is actually covered in what is known as green patina. And this green patina is because the copper, which is the main material that the Statue of Liberty is made out of, it has actually undergone an oxidation reduction reaction. So let's actually explore the reaction that happens. In the picture that you see on the right, that's the Statue of Liberty. Below, we can see the chemical reaction for the copper that is the material from that the Statue of Liberty is made out of. So overall, the copper that is the material from the Statue of Liberty, because of its exposure to the oxygen in the air, it has formed copper 2 oxide. And that copper 2 oxide is that green tint that the monument has. Overall, what we observed is that elements by themselves don't have an oxidation number, so they have an oxidation number assigned of 0. And then in the product of the reaction, we can see how copper now is in an ionic compound. So copper went from an oxidation number of 0 to an oxidation number of 2. We're going to learn soon how to assign oxidation numbers. And then oxygen went from an oxidation number of 0 to an oxidation number of -2 because of how it looks in the product. So anytime a substance or an element for that matter in the reactants undergoes oxidation, it means that it's going to be losing electrons. Copper, we know it undergoes oxidation because if it loses electrons, then it's going to become more positive. And you could see it in the charge, but you could also see it in the oxidation number that it has in the product. On the other hand, oxygen actually undergoes reduction because we can see how oxygen in this actually went from an oxidation number of 0 to an oxidation number of -2 because of the product and the reaction. And something that accepts or gains electrons is going to undergo reduction. So that's why we can observe that overall in this reaction, since oxygen went from an oxidation number of 0 to -2, it undergoes reduction. Let's now explore how do we determine oxidation numbers for chemical reactions. So when it comes to this, there's actually rules for calculating the oxidation numbers, okay? These general rules, you see it summarized in this slide. Rule number 1. If you have an element by itself, its oxidation number is 0. This includes the diatomic elements. So that is H2, N2, O2, F2, Cl2, Br2, and I2. Whenever you see them by themselves in a chemical reaction, then you know that their oxidation number is 0. If you have monoatomic ions, meaning elements that live in groups 1A, 2A, 3A, but this only applies for aluminum, gallium, and indium. Or if you have elements in 5A, specifically nitrogen and phosphorus, in 6A, oxygen, sulfur, or selenium, in 7A, fluorine, chlorine, bromine, and iodine, that monoatomic ion charge is going to be their oxidation number. So for example, as you can see here in the second bullet point, if things live in group 1A, their oxidation number is always +1. Group 2A, always +2. Group 3A, aluminum, gallium, or indium, is going to be 3+ in their oxidation number. Then for 5A is going to be -3, their oxidation number. 6A is going to be 2 negative, and 7A 1 negative. Remember that when we're talking about monoatomic ions and charges, this is going to refer in general whenever they're present in ionic compounds, okay? So as I just discussed, remember that halogens live in 7A. That's why there's a -1 charge. And then we see what happens to things in 6A, like oxygen, that is going to be an oxidation number of -2. Fluorine, because it's part of the hydrogen of the halogens, it's -1. And it is important to note that the sum of the oxidation numbers for a neutral compound is going to equal 0. And the sum of the oxidation numbers for a polyatomic ion is going to equal the ion charge. So let's go over the following example for oxidation and reductions so we can actually determine what gets oxidized and what gets reduced. So in the following reaction, we have iron 3 oxide reacting with carbon, making iron and carbon monoxide. As you can see, this is a single replacement reaction. So in this single replacement reaction, we need to identify which substances in the reaction are elements by themselves. And that will be the first thing that we determine their oxidation number. So in this example, carbon by itself, oxidation number of 0. Iron by itself, oxidation number of 0. Then we have to explore if we have monoatomic ions. Most monoatomic ions, we're going to see them in the context of ionic compounds. So take a moment and determine between Fe2O3 and CO, which one is an ionic compound. Fe2O3 is the ionic compound. So if I make that chemical formula be changed into ions. Then this is Fe plus 3, O minus 2, and their monoatomic ion charge is their oxidation number. So that means that Fe, your iron, its oxidation number is positive 3. The oxidation number of O2 minus is negative 2. Next, we are going to deal with the covalent compound carbon monoxide. For covalent compounds is a little bit different. When we're trying to determine their oxidation number, the first thing we do is that we assign the oxidation number for the second nonmetal in our molecule. So when it comes to this, in the molecule carbon monoxide, oxygen is your second nonmetal. We can see that there's a rule that establishes that oxygen is minus 2. So that is its oxidation number, negative 2. There's a rule here that establishes that if you have a neutral compound, so something that doesn't have charge, the sum of the oxidation numbers needs to equal 0. So if I know that I have an oxidation number of minus 2 for the oxygen, and I only have one oxygen, since I have one carbon, what will be the oxidation number of carbon in carbon monoxide? If you answered positive 2, you are correct. Because what happens overall is that positive 2 added to the negative 2 makes the oxidation number equal 0. So that is correct. So now that we have assigned all of our oxidation numbers, we can actually make a table. And in this table, we are going to write our findings. For this reaction, we have iron, oxygen, and carbon. We have the reactant signs, and we have the products. I'm going to write what is the oxidation number of all the components that I have in my reaction. In the reactants, iron has an oxidation number of +3. Oxygen has an oxidation number of -2. Carbon has an oxidation number of 0. In the product, iron has an oxidation number of 0. Oxygen has an oxidation number of -2. And then carbon has an oxidation number of +2. So I can observe here what happens overall. If I do a number line where I say any value to the right of the 0 is positive, any value below 0 is negative, any element that their oxidation number went from positive towards 0 or from 0 into the negatives, that means that it undergoes reduction. Anytime you have an oxidation number fluctuate from a negative number towards positive or from 0 towards a positive, that means that that element undergoes oxidation. So here we can observe that in the case for the iron went from positive all the way to 0. So its oxidation number is moving in this direction. So what this is suggesting is that iron undergoes reduction. And then we have oxygen. As you can observe, oxygen doesn't have a change in its oxidation number. So that means that we consider those the spectator atoms. Spectator atoms are just looking at the reaction happening, but they are not losing or gaining electrons. If we look at what happened to carbon, carbon started at 0 and went into a positive value. So what that means is that in this reaction, carbon actually is undergoing oxidation. Let's actually do at least one more example to solidify this concept of oxidation number. Let's say that we are going to be looking at the first reaction that we have here. Magnesium reacts with HCl to make MgCl2 and H2. So what's happening overall is that we need to assign the oxidation number for any element that it is by itself. So we can see that in the reactant, magnesium is by itself. So that's an oxidation number of 0. In the products, we see that hydrogen, since it's diatomic and it is by itself, it has an oxidation number of 0. Out of the two compounds that we have here, magnesium chloride is ionic. And if I break it into ions, this is going to be Mg plus 2, Cl minus 1. And that's going to be their oxidation numbers. Because monoatomic ions, their charges is their oxidation number. So what that means is that magnesium oxidation number is plus 2. Chlorine oxidation number is minus 1. Let's move on to the reactants. In the reactants, we have a covalent compound that is HCl. And then in terms of HCl, the second nonmetal is Cl. Cl lives in group 7A. That means that its oxidation number is going to be its charge. So that means that the oxidation number for Cl is -1. Hydrogen, when we add its oxidation number to the oxidation number of Cl, it must equal 0. And in addition, hydrogens have an oxidation number of +1. So we put +1. Now we make our table. We have reactants. We have product. And then here we have magnesium, we have hydrogen, we have chlorine, and we observe what happened with them in the reactant versus the product. Let's write in our findings. Magnesium starts with oxidation number of 0. Hydrogen has an oxidation number of +1. Chlorine has an oxidation number of -1. Then we proceed to magnesium turns into +2. Chlorine has an oxidation number of -1. Hydrogen has an oxidation number of 0. Take a moment and identify the element that is the spectator atom. So if you determine that the spectator atom is chlorine, you are correct. Next, let's classify what happens with magnesium and what happens with hydrogen. As I mentioned, I can do a number line where this is 0, this is positive, this is negative. Anytime that we have a shift in the oxidation number in this direction, that means reduction. Anytime it happens in this direction, that's going to be oxidation. So if we look overall for this problem, when we looked at it closely, we can see how magnesium started at 0 and it went positive. So it's moving in this direction. So that's why oxidation is what's happening to magnesium. On the other hand, for hydrogen, it started positive and it went to 0. So that means that it's undergoing reduction. Make sure that you practice with the second problem that you see on this slide.